The Webb Telescope detected methane and carbon dioxide in the atmosphere of exoplanet K2-18b. Data obtained by the James Webb Space Telescope indicate the presence of carbon dioxide and methane in the atmosphere of exoplanet K2-18b. Moreover, this extremely sensitive observatory detected traces of dimethyl sulfide. This compound is produced on Earth by living organisms. K2-18b was spotted in 2015. Researchers then determined that it was orbiting in the habitable zone, a place in orbit around a star where conditions could be favorable for the emergence of life. The most important element of the ecosphere is the possibility of the presence of liquid water, which is a key element in maintaining conditions favorable to life. At least life as we know it. Further research also discovered water vapor there, also indicating the presence of hydrogen and helium in the planet's atmosphere. This suggested that the planet might be covered with oceans. That's why astronomers pointed the James Webb Space Telescope, JWST, at it. The observation data allowed us to determine that the exoplanet contains carbon dioxide and methane molecules. K2-18b orbits a white dwarf called K2-18, located in the constellation Leo, 120 light-years from the Sun. The exoplanet is about 8.6 times more massive than Earth. K2-18b was first observed using the Hubble telescope. Since then, this world has fascinated scientists, who have debated the possible composition of the atmosphere of similar objects. Some astronomers believe that planets like K2-18b are promising places to look for signs of extraterrestrial life. Previously, we focused mainly on smaller, rocky objects. However, we also need to take into account larger planets because it is easier for us to study the composition of their atmospheres, explains Niku Madhusudan, an astronomer at the University of Cambridge and the main author of the article describing the discovery, which will soon be published in the journal, the Astrophysical Journal Letters, and can now be read. See the archive preprint database. The abundance of hydrogen, methane and carbon dioxide and the lack of ammonia support the hypothesis that there may be water on K2-18b. Webb's initial observations also enabled the detection of dimethyl sulfide, CH3, 2S. On Earth, it is produced mainly by phytoplankton. However, this does not mean that there is life on the exoplanet. Even if there are oceans full of water on its surface, it may be too hot or too cold for any organisms to survive. There are no similar planets in our solar system. But these are the types of exoplanets we detect most often, explains study co-author Subhajit Sarkar from the University of Cardiff. Characterizing exoplanet atmospheres, i.e., identifying the substances and physical conditions found in them, is a dynamically developing area of astronomy. When a distant planet orbits its parent star, it temporarily obscures its glow. During similar transits, a small portion of the light emitted by the star passes through the exoplanet's atmosphere. This leaves traces that are captured by telescopes and then analyzed by scientists. We were only able to make the discovery thanks to the incredible capabilities of the Webb Telescope, including its unprecedented sensitivity and extended range of recorded wavelengths, says Madhusudan. In his opinion, just one observation with Webb provides more information than years of research conducted by Hubble. Our work is the result of just 2 observations of K2-18b by the Webb Telescope. This is only a demonstration of the capabilities of this telescope. There are still many discoveries ahead of us regarding the atmospheres of exoplanets located in habitable zones. Numerous studies are underway, says co-author of the article Savas Constantinou from the University of Cambridge. The team still intends to observe K2 to 18b. Our goal is to prove that there is life on distant planets. This would change everything in our understanding of reality, concludes Madhusudan. When did our ancestors start wearing shoes? When did people start wearing shoes? New research suggests that our ancestors may have been wearing shoes around 100,000 years ago. This is indicated by fossil traces found in South Africa. When and where were shoes first designed? The answer to this question is not easy. Determining when people started wearing shoes is a challenge. There is no point in looking for physical evidence, because to be comfortable, the footwear had to be made of materials that have not been preserved in the fossil record. Ethnology comes to the rescue, a science that studies fossil traces. Over the last 15 years, we have identified over 350 vertebrate track sites along the South African coast. These include numerous traces left by people who clearly walked or ran barefoot, as evidenced by toe prints. But we also noticed similar prints without visible fingerprints. Also realizing that very little research has been done on the origins of footwear, we decided to investigate further, said Charles Helm of Nelson Mandela University in South Africa. Scientists began by determining when and where our ancestors had the technology to create tools that could be used to sew and make shoes. They even created shoe models that could be made simply and with simple tools. They also analyzed archaeological sites where traces of our ancestors were found. The results of these activities suggested that the best place to look for traces of shod hominins was Western Europe and the coast of South Africa. Most of the traces examined by scientists date back to approximately 70,000 years ago, up to 150,000 years. 3 from this period have been found in South Africa and may have been created by booted people. While reviewing various studies on this topic, scientists came across 4 more archaeological sites where similar traces were found. They are younger than those from South Africa, because they are over 30,000 years old. All of them come from Western Europe, including one site attributed to Neanderthals. Although the evidence is inconclusive, we are excited by our findings. They support the view that the southern part of Africa is a region where human cognitive and practical abilities developed a very long time ago, Helm admitted in the conversation. The researchers focused on these 3 tracks from South Africa, which were most likely left by hominins and were clearly outlined but did not contain fingerprints. Scientists turned to the Bushmen, also called San, who inhabit the southern parts of the Kalahari Desert. They are considered one of the oldest peoples in the world. Scientists were interested in their sandals. By analyzing them, scientists wanted to find out what ancient footwear might have looked like. They also checked what the footwear worn by the characters recorded in various examples of rock art of this people looked like. They also got acquainted with the oldest preserved examples of this type of footwear. We created different types of footwear and used them to create footprints on beaches and dunes and then analyzed them. These experiments showed that the design of an open, hard sole, leaving traces on moist, moderately soft, but still cohesive sand, best fits the traces from the 3 studied sites, Helm noted. Typically, the presence and alignment of fingerprints is a key factor in identifying hominin tracks. It is unlikely that such features were present in the footprints of shoe-wearing ancestors. We had to make sure that the findings indicating shod hominins were genuine and not the result of poor track condition or erosion, Helm wrote in the conversation. While our evidence is suggestive, we do not yet consider it conclusive. We are looking for further sites that, ideally, in addition to being in a good state of preservation, would contain a series of traces enabling detailed analysis. Helm noted. Astronomers presented a project to build a giant telescope on the Moon. We have built telescopes in various places on Earth, and even sent some into space. Each of the new telescopes, packed with technological innovations, resulted in amazing discoveries about the universe. So what should be the next observatory that would significantly expand our knowledge? A recent publication suggests that a good place to build one would be the surface of the Moon. A team of astronomers presented a project to build a huge optical telescope in one of the craters at the lunar pole. According to the authors, it could take space observations to an unprecedented level and change the way we study the universe. Telescopes can be found almost everywhere, from backyards to mountain peaks to the most remote islands. We also send them into Earth orbit. So why not try placing one on the surface of our natural satellite? Moreover, such an idea is by no means new. However, the question arises, what kind of telescope would we be able to build there? And is it even possible? We can find quite a lot of examples of such initiatives from the past. For example, NASA once funded a grant aimed at examining the feasibility of implementing a project called the Lunar Crater Radio Telescope, LCRT. Moreover, proposals to construct this type of telescope appear much more frequently among scientists. In turn, already during the Apollo mission, astronauts placed the so-called retroreflectors. And thanks to them, it became possible to determine the distance from the Moon to the Earth with an accuracy of millimeters. Sometimes it is also called Life Finder Telescope at Lunar Poles, LFTALP. It would be an array of telescopes with a diameter of 6.5 meters, the purpose of which would be to study the atmospheres of exoplanets as they pass in front of their stars. But there are many more possibilities. For example, Lunar Optical UV Explorer, LOUVE, which would be used to study bright objects visible in ultraviolet. Or even a gravitational wave observatory. However, all these proposals have one thing in common. Building them on Earth would be quite a challenge, let alone on the Moon. Therefore, it would be better to focus on something simpler but feasible. By the way, you could try to use the shape of the Moon's surface for this purpose. And it could be an ordinary optical telescope. On Earth, the power of a telescope depends on the size of the primary mirror and the focal length, which can be increased by adding additional mirrors. On the lunar surface, however, a row of mirrors arranged on a crater could be used as a primary mirror. Moreover, the use of the crater would significantly reduce the amount of work necessary. In such a situation, the detectors could be suspended on a cable. This solution was used in the case of the Arecibo Observatory. The construction would be relatively simple because the mirrors in question would not have to be large. It would also be possible to use a certain variation of this idea. Well, the mirrors could be placed on one side of the crater and the necessary instruments on the other. Of course, in each case, issues such as ongoing dust removal and seismic protection would have to be planned. Therefore, it would still not be an easy task.